In this video, we're going to do another curve sketching problem, and as before, the first thing you want to do is you want to find the domain. But here it's pretty obvious the domain is everything except for -2 and +2. So pretty quickly we get that the domain is from -infinity to -2, union -2 to +2, union 2 to infinity. And so that is our domain. For horizontal asymptotes, we notice that limit as x goes to positive or negative infinity, both of these, of the function f of x here, so 1 over x squared minus 4, both of these go to 0. So we get a horizontal asymptote of 0. For vertical asymptotes, we want to notice that limit as x goes to -2 from the left of this function, x squared minus 4. Well, what is that approach or go to? If we have -2 from the left, that means these are slightly bigger than 2 here, but more negative. The absolute value is slightly bigger than 2. So when we square it, we're going to get slightly bigger than 4. So this denominator is going to be positive, but approaching 0. 1 over something approaching 0 is either infinity or negative infinity, but since it was positive, this approaches positive infinity. Then similarly, the limit as x approaches -2 from the right. Well, now we're going to approach it from the other side. These are going to be just smaller than 4, so these are going to be negative in the denominator. So this approaches negative infinity. We can have a very similar argument for approaching +2 from the left, in which case we're going to get negative infinity, and the limit as x approaches +2 from the right is going to be positive infinity. And so this gives us vertical asymptotes at -2 and +2, and moreover tells us the behavior as we approach those values from each side. All right, so now that we've dealt with the domains and the asymptotes, we need to find the first derivative. All right, so this is really x squared minus 4 to the negative first power. So really we get -1 times x squared minus 4 to the negative second times the derivative of the inside, which is 2x. So this is -2x all over x squared minus 4, quantity squared. Okay, let's figure out our intervals here. Well, actually, let's figure out our critical points. Well, first off, we already have the domain broken up by -2 and +2. But we also get this extra critical point of c equal to 0 because this derivative is equal to 0 when x is 0. All right. So then we do our intervals check here. We notice that, let's see, -2x, and let's see, x squared minus 4, quantity squared. All right. So we have -2x divided by this thing, the x squared minus 4, quantity squared. So that quotient there, we can determine if it's positive or negative just by determining the positive or negativeness of each of these separately. So from -infinity to -2, we plug in a negative value. This is a positive. -2 to 0, we plug in a negative value, that makes this a positive. Plugging in a positive makes this term a negative, makes this a negative. Then we plug in anything into here, and we're going to get a positive because it's whatever squared. It's something squared, right? So we just get a bunch of positives, which tells us our first derivative is a positive divided by positive. So a positive, positive, negative, negative. This tells us our function is increasing, increasing, decreasing, decreasing. And that is our intervals of increase and decrease. All right, so then let's do the second derivative. f double prime of x is equal to... All right, to do this, we need to take the derivative using the quotient rule of this right here. So we get the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. All right, so we get at least one x squared minus 4 factor in each of these terms. So one of them cancels out here, one cancels out here, and one cancels out here. So we're left with f double prime of x is equal to, all right, we get negative 2x squared plus 8. And then over here we get a positive, and then 2x times 2 times 2x is positive 8x squared, all over x squared minus 4 cubed. This is 6x squared plus 8 all over x squared minus 4 quantity cubed. All right, we want to know when this is 0, or if the derivative doesn't exist, but the only place the derivative doesn't exist is at negative 2 and positive 2, where we aren't even in our domain anymore. So we aren't really including those points, or we don't need to include those points at the moment. So really, we just need to determine when the second derivative is 0, but 6x squared plus 8 is never 0. All right, so we have no critical values for the second derivative. All right. So now we just need to determine our intervals here. So we have the interval from negative infinity to negative 2, from negative 2 to positive 2, and 2 to infinity. Well, 6x squared plus 8 is always positive. We already said that. It's never 0, right? So that's always positive. And then the denominator, x squared minus 4 quantity cubed. Well, this is going to be positive between negative infinity and negative 2. It's going to be negative between negative 2 and positive 2, and positive when x is bigger than 2. So this tells us our second derivative is positive, negative, positive, which tells us that our original function is concave up, concave down, concave up. All right. Now, if we go back up here, actually, real quick, we can talk about this. Even though we change from up to down and down to up here, there is no point of inflection because negative 2 and positive 2 are not in our domain. If we go up here, we did have one point where we switched from increasing to decreasing. So does that imply that we have a local maximum? Well, at 0, which is where this occurs, our concavity is down. So using our second derivative test, that does in fact imply that 0, negative 1/4 is a local 0, negative 1/4 is a local maximum. So I want to go ahead and plot all of that information. So I'll sketch that over here. At negative 2, we have an asymptote. At positive 2, we have an asymptote. At 0, we get a y-intercept at 0, negative 1/4. All right. As x approaches negative infinity, we approach 0, and we are, from negative infinity to negative 2, we are concave up and increasing, and the function shoots off towards positive infinity as x approaches negative 2 from the left. Putting all that together, we get a shape like that. Between negative 2 and 0, we are concave down and increasing. So it looks like this. And moreover, as we approach negative 2 from the right, we approach negative infinity, so this shoots off downward. As we approach positive 2 from the right, we again go towards negative infinity. And also, in this interval from 0 to 2, we are concave down and decreasing. Oops. And that can be better drawn. There we go. And then finally, from 2 to infinity, we are concave up and decreasing. Moreover, we limit to 0 as x goes to the right, or to positive infinity, and we limit towards positive infinity as x approaches 2 from the right. And so we get this as our sketch of the graph. And that is where we will end this video.